Hi everybody, today we will look at mathematical induction, and the principle is illustrated by these domino blocks. And of course it's the idea that if you topple one domino block, the other ones will topple, and eventually they all will topple. So let's assume there's n blocks, n of them. The mathematical induction principle says that if we prove that the first one topples, so the statement is true for the first one, n equals 1, and then after that we can prove that assuming any of them topples, for instance that one, or that one, or that one, assuming that that one topples, we can prove that the next one topples. So n equals k, assume n equals k is true, then prove it for k plus 1. If you do that, you're full circle, because you can say, oh, the first one topples, and if any topples, then the next one will topple, so therefore they will all topple. That's mathematical induction in a nutshell. As an example, we'll go to the next. Here on this slide, we will prove that 4 to the power n plus 2 is divisible by 3 for all n bigger or equal 0. So we will use induction to do that. Now first of all, realize that if something is divisible by 3, it has to be a multiple of 3. So we're looking for multiples of 3. So that is expressed as 3 times a, where a is any whole number. In this case, z plus probably. So if a is an integer, a whole number, then 3 times a is a multiple of 3. That's important. Now the first step is to show that the statement is true for the smallest n possible, which is 0. So for n is 0, we have 4 to the power 0 plus 2. Now that is 1 plus 2 makes 3, which is 1 times 3, hence divisible, a multiple of 3. So the first step is proven. The second step is the assumption that n equals k is true. So we will assume that 4 to the power k plus 2 is a multiple of 3. So that can be expressed as 3a in our case, a multiple of 3 whereby a is any integer. So we assume, oops, what happened there? Assume that this is true. Okay, and we will use this a bit later. We will use this in the third step, in step 3, where we look at n equals k plus 1. So here we say 4 to the power k plus 1 plus 2 needs to be a multiple of 3. Now I'm going to rewrite this. 4 to the power k plus 1 is 4 times 4 to the power k plus 2. And now I'm going to use the assumption here in part 2, and I'm going to rewrite it as 4 to the power k is 3a take 2. So I've isolated the 4 to the power k part as 3a take 2. This is the creativity that you need to have with mathematical induction. And I'm going to now substitute this into 4 to the power k. So what I get is that it is 4 times 3a take 2 plus 2. Now I can work that out further, and I can say, that's 12a take 8 plus 2, that's take 6. And then because I'm interested in multiples of 3, and here's again a creative step, I'm going to write this as multiples of 3. So I'm going to look for 3 as a common factor. And I can because it's 3 times 4a take 2. Really the last bit is realizing that what I have here is an integer. Because I know that a is an integer, so 4 times a is an integer, and 4 times a take 2 is an integer. So in other words, what I'm saying is that 4 to the power k plus 1 plus 2 all the way through here can be expressed as a multiple of 3. So a big tick there, because that's exactly what we needed to prove, that it is a multiple of 3. And it assumes that 4 to the power k plus 2 is a multiple of 3. So assuming step 2 is true, then we have now proven step 3 is true. So now we can say, as a final, since P0 is true, so the first step, n is 1, n is 0, and pk plus 1 is true whenever pk is true, pk plus 1 is true whenever pk is true, that means that Pn is true for all n bigger equals 0, because we started at 0. So there you have mathematical induction.